Well, hello again, everybody. Well, I was playing around the other day with that inverter, wasn't I? And yeah, kind of chasing my own tail as usual. And one of the things I found is that this AC plug-in power energy monitor was getting very hot, and I think I came up with lots of speculation why it was getting hot, and yeah, probably barking up lots of wrong trees. Oh, there's a screw missing out of there. Must have took that one out earlier. And well, you start second guessing yourself, and I actually wanted to try and find out what it is that's getting hot, very hot in here, because there is something getting hot, but yeah, I'm not sure what. Now, I think I said last time, it doesn't appear to want to come apart, this thing. Screw there I can possibly get out, and there's a screw there, but there's some screws that are kind of right in the middle of the board, so I've got no idea how you could possibly get at them. Maybe it was all glued together. So it looks like what I can see in here is I can see this this green thing. What's I call it, green thing? I'm guessing this is the capacitive dropper which this thing employs. I can also see a if I look from the other side, I can see this loop here, which I'm guessing is the current shunt for when this measures the currents. And I can also see a resistor, and it looks like this. Just lost another screw. Yeah, so we're going to have one screw to put back in here. I think that's how I lost the other one, actually. So it looks like, yeah, sorry, it's not making for great video, is it? I suspect that this resistor here is maybe the anti-surge resistor. And I think I can also see a couple of maybe precision resistors in here. So I think what we'll do is we'll plug this into the inverter again and, well, let it fry itself. Let's see if we can figure out what's getting hot. And we'll have a poke around with Mr. Good old thermocouple meter. So ambient temperature in here is about 19 degrees. It's absolutely freezing outside. Oh, it's going down 18 degrees, 17 degrees. Yeah, it's a bit cold in here. It's absolutely bitterly cold outside tonight. I think it's about -1 at the moment. Right, okay, so let's just give it a few seconds and see if we can figure out what's getting hot. I suspect that what's getting hot is this this surge limiting resistor here, and that's my bet. So what we'll do is we'll just prod this inside, and yeah, hope I don't touch anything live. I should be okay. It's this isn't referenced to ground because it's being fed from the isolated bench power supply, and yeah, I think we're going to be fine. Anyway, let's switch it on. Famous last words, eh? So we're at 24 degrees at the moment. 28, 31, 33, 34, 36, 42, 44, 50 degrees, 60 degrees, 67 degrees. Well, this has been on probably about 30 seconds in total, and this resistor's up at 74 degrees now, and it's still climbing, and I don't think it's showing any signs of stopping. And it's just starting to liberate, you know, that lovely burnt, dusty smell that you get from hot electrical equipment, hot resistors burning off the dust. So that's at 88 degrees at the moment. Let's just cool that down. Is the capacitor getting hot? No, that appears to be cold. There's another resistor tucked down here. Is that getting hot? No, not particularly. Let's go back and test this one at the back. So 92 degrees, still climbing. Again, we've probably been on about a minute now. So we know what's getting hot. It's this resistor here, and that resistor is there as kind of a transient limiter. It's designed to, let's just turn that off because it smells quite hot. The purpose of that resistor, it's really just designed for kind of like the high-speed transients you get whenever you plug something into the mains. You obviously get a sudden inrush of current, or you do with a capacitor, because you know if you plug something in at the top of the mains cycle, you're going to go from 0 to 300 and something volts in no time whatsoever when you put that plug in. So the purpose of that resistor, it's designed to just limit the maximum inrush current. Well, this has been unplugged about 5 minutes, and this resistor is still very hot. So what I think we need to do now is, rather than plugging it into the inverter, I just need to do kind of a sense check, if you like, and plug it into the normal mains. And I'm guessing that if we plug it into the normal mains, this resistor won't get hot. I mean, it might get a little bit warm because it is a power resistor, but I'm guessing it isn't going to get scorching hot like it was before. And I think that what that will be telling me is that this capacitor is probably letting a lot of current through. Because the normal main cycle coming out of the plug, it's obviously a nice smooth sine wave. So this capacitor will be acting as an impedance, or probably easier to say acting as a resistance, and it will actually be limiting the current which this resistor actually sees. But if you actually have these, if you remember the horrible kind of square wave output coming from this inverter, that's going to go straight through that capacitor, and probably the only limiting thing in this circuit, the only thing that's stopping this circuit from being fried, is this 100 ohm resistor there. So let's just plug it into the mains, into the normal mains plug, and see if it still gets hot. At the back of my bench here, I've actually got an isolated socket fed from an isolation transformer under the bench. I don't use it very often, but it's come in handy recently. Even when I'm using this isolation transformer, you've still got to be a bit careful with main stuff. It's funny, at work, I do a lot of high power industrial electrics, and I'm always messing around with three-phase motors, or I used to, and motor drives and laser power supplies and things, and kind of do that without a second thought. But messing around with stuff on the bench, I always like to be a bit careful. Right, okay, let's just see if that's cooled down. Okay, this resistor's about 23-24 degrees, just sitting at just cooling down basically from being hot before. So let's switch the mains plug on, and hopefully this thing isn't going to get so hot this time. Well, as you can see, it is warming up, but I don't think it's warming up at anything like the rate it was before. What I'll do is I'll just wait for 5 minutes and I'll bring you back. Okay, well, we've had this on for about 5 minutes now, and this resistor's now just reached 33.5 degrees, and it's still climbing very slowly, but yeah, it's certainly not running away like it was before. I mean, in just a minute this resistor was up at 90 degrees when it was plugged into the inverter, and now just running off the normal mains, it's only at 34.5 degrees, and it's run for 5 minutes. So it clearly demonstrates that when we plug this type of when we plug this power plug, this energy monitor, when we plug it into the inverter, it really doesn't like it. It doesn't like it at all. And as I say, I speculate it's just due to the use of this capacitive dropper circuit, which is just letting through all the very sharp current spikes which are coming from the inverter. So maybe the next thing to do is just have a look at that again. So I guess we can screw this back together now using the one screw. Well, I lost that last remaining screw, so we now have no screws. Okay, all par for the course, isn't it? But yeah, that's what tape was invented for, wasn't it? Well, I'm sure that you'll remember in last week's video we used the AVO 8 meter to measure the voltage and the current across the this little dummy test circuit that we made that had a a capacitive dropper and an LED. And I got some readings which I really couldn't explain very well. And I kind of thought I had the answer, and I just thought it was down to the meter not being a true RMS meter. But I think there's perhaps a little bit more to it than I first realised. So if you don't mind, I think we'll just dig a little bit further into RMS meters, not RMS meters, and probably the limitations of what RMS meters do, because you may think you're using a meter that's a true RMS meter, but maybe you're not. So what I think we'll do this time is, rather than just using the little LED circuit with a capacitive dropper, we'll actually use the true energy monitoring plug. Because that's the thing that's kicked all this off, isn't it? So that's what we're actually going to be used to measuring the current consumption and the voltage that's being supplied to this. And we're going to do the measurements, one with the power plug being fed from just the mains. And then for the second test, what we're going to do is we're going to take the voltage and current measurements again, but we're going to do it when the unit's being fed from the inverter. And I think what we'll find is we're going to get some quite different readings, which I don't think are going to be particularly surprising, because again, I think everybody who watches this video, you all know the difference between RMS and true RMS and well, let's just call it non-true RMS meters. I don't think I need to explain it, because you people are going to know the difference. But what maybe you'll find more surprising is the limitations of so-called meters which claim to be true RMS. It's something which I really just hadn't considered before. I mean, I'm guessing it's quite obvious when you know about it, like most things are, but it wasn't obvious to me before I actually started making this video. So we'll have a quick look at that as well. So what have we got to use today? Well, we're going to use our AVO 8, which it's not a true RMS meter. We're going to use the Tech 4 meter, if I can find it, which is this, made by Ryobi. That's also not a true RMS meter. We're going to use the Fluke 75, which claims to be a true RMS meter. We're also going to use the BK Precision 5491A, which let's get that in shot. Which this one and the 5491A claims to be a true RMS meter. We're also going to have a go with the Exotec 380820, which isn't actually a meter. What it actually is an AC source, but it can actually measure the current, the voltage, the phase, the power factor of the load it's supplying. So a little bit of a wild card. And we're also going to use an oscilloscope to have a go at measuring it. And we're going to use the old Tektronix scope, because again, I'm a little bit precious about putting mains voltages up some of my other scopes. So we're going to use the TDS 2022B made by Tektronix. I've had this many years and I quite like it. So, sorry, the Fluke, yes, that's true RMS. The BK Precision, yes. The Exotec is a true RMS meter on it. And the TDS 2022B, I believe that can also measure RMS. When we use actually the oscilloscope to measure the current, we're going to have to cheat a little bit, and we're going to have to just develop some current across a load resistor, which is going to skew some of the readings slightly. I think somewhere, probably at work, I've probably taken it into work and somebody probably robbed it. I do actually have a current Tektronix clamp probe somewhere when I used to play about with switch mode power supplies and things, but I've had a look around here for it, and it's probably at work. I've probably got twice as big of store equipment hidden away at work than I have in my workshop at home. So I wasn't able to put my hand on the on my current probe meter for the scope, so we're going to have to frig that, and we're just going to have to develop the current across a load resistor. But that's quite an interesting little thing to do as well. So we're going to conduct all them tests first of all using 230 volt mains. And then we're going to repeat effectively the same test using the power from the inverter. The only thing that we won't be able to do is, obviously, we won't be able to use the Exotec 308820, because as I said, that's the source. So yeah, that can't output a square wave. It can only output a sine wave. But we can do all the other measurements. So let's crack on. I'm afraid this is all going to be a little bit messy. What I'd like to try and do is keep everything around 230 volts for both tests, because I think that inverter was outputting about 230 volts measured with all the meters. So I'm going to say that the 230 volts, I'm going to use that as kind of my reference level. But unfortunately, the mains output from my plugs here is it's a lot higher than that. It's around 250 volts. It might be 254. And I think even the isolation transformer I've got probably steps it up just very slightly. Maybe there's a couple of extra windings on it. So it's all going to be a bit convoluted. We're going to come out of the isolating transformer and we're going to go into the variac, and then we're going to go into everything under test. So let's try and get all this set up. You could do some of these tests without the isolating transformer, but not when I try and measure the current using the oscilloscope. So that's why I'm setting it up now. Everything's going to be run from the isolation transformer. Now, you don't need an isolation transformer when we're doing the test using the inverter, because the inverter is actually going to be fed with a 12 volt power supply, and it's a 12 volt switch mode power supply that I'm going to be using, but the outputs on that switch mode, they are fully isolated, so nothing will be referenced to ground. So again, because I know that newbies won't be watching the video, I don't need to go into that. You guys understand it better than I do. So it's one of them things that if you're not sure, don't do what I do. Let's chat, let's face it. I'm not a good example of how to do things. You'll probably end up electrocuting yourself if you follow my examples. I electrocute myself all the time. Right, so what do we need? Let's turn that off before I confuse myself. So we need to get the power out of this thing. So we're going to use this little def adapter. Oh God, remember them 5 amps, 5 amp plugs. What a useless connector. I think we'll use the fluke meter kind of to keep everything straight. We'll use that as our reference. Don't know if that's a valid thing to do or not, but that's what I'm going to do. So we're going to come out of here. So I think the first meter we'll use to do the current measurement on, we'll use the AVO meter, because, well, that's what I've got written down on the bit of paper, so we'll use the AVO. So I've got to remember how to use these things, AVOs, AC, and we'll try the, we'll put it on the 100 milliamp, 0.1 amp range. Okay, does that look right? Somebody tell me before I switch it on. Yeah, probably okay, innit? Start by switching that off. So turn that on, turn that on. Let's turn this off to start with. Turn that on. Oops, don't want you on ohms range. That's not a good idea, is it? Did anybody shout then? Did anybody shout you've left the meter on ohms? I bet you didn't, did you? Okay, we've got some voltage going up there. So it's interesting to see what this thing actually powers up at. Oh, it's actually drawing current already, so the display's not lit up, but we're drawing, what's that? We're drawing just under 10 milliamps. Alright, 230.3. The meter itself is showing 229.9. I probably should write these down. Probably I should have put a line on my chart for the voltage and current measurements for this thing, shouldn't we? I'm going to say the fluke voltage measures 230, and we'll just round it up to the nearest volt. And the AVO 8, I'm going to have to just measure the current for that. It's showing, excuse my head, turn my glasses off, try to, 46 milliamps. So the AVO current is showing 46 milliamps. What I'm going to do is I'm just going to go ahead, I'm going to populate the rest of this table now. I'm going to use the various instruments here to take the voltage measurement across the plug and the current measurement that it's drawing. So I'll complete this chart and I'll bring you back. So this is the Ryobi Tech 4 meter measuring the current, and that's measuring 46.2 milliamps. And an interesting thing on this meter, both the volts and the milliamps share the same input connector. So if you just happen to turn this selector switch too far, that could really ruin your day, couldn't it, if you were trying to measure mains voltage, because you'd just got that set in the wrong position. So yeah, I'm not sure that's such a great feature, although I've got to admit changing leads over is a constant pain in the arse, but yeah, it's probably safer than that. Oh well. So we've kept our 230 volts, that hasn't changed, and the current reading is 48.6 milliamps. So that's our current measurements completed for everything apart from the oscilloscope and the Exotec, and we're going to use a slightly different test setup to do that, so we're going to leave that for a moment. So let's swap over to our voltage measurement. I've actually just got the Avo 8 to do and the Tech 4 because I was swapping these meters out before, so I took some voltage measurements for them earlier. So we'll just do the Avo and the Tech 4 now. So let's just take the voltage measurement off the Avo 8, and that looks like it's pretty much bang on 230 volts. Now just make sure when you're looking at the meter on your screens, just move your head slightly to one side, because you just need to make sure that you've just lined up the pointer with the shadow, with the reflection in the mirror. So are you doing that? Just move your head. No, you need to move your heads to the right. No, that's left. Move it to the right. Good. Right, you've got that. So the Ryobi Tech 4 is reading 229 volts. So we've just switched over to the Exotec, this universal power source analyzer. So this is not a voltmeter or a current meter. It will actually supply various frequencies, 50, 60 hertz at various voltages. So I just thought I'd throw it in as a bit of a wild card because you haven't seen it before. I just noticed at the moment it's just displaying the input line voltage, which at the moment is 243 volts, which is you know, kind of interesting. As I say, my mains voltage is all over the place. Yesterday when I was in the lab it was 254, but today it's back to 243, so it does jump around a little bit. But what we'll actually do is, just so we're on a even playing field, we're going to use this front socket. So if I just switch over to the front socket, this is actually now outputting a voltage on here which is will be bang on 230 volts. So let's just switch that on, operate. And so it's going to give us quite a few things. It's going to be outputting 230 volts here, and it will be it'll give us a milliwatt reading, it'll give us power factor, frequency is 50 hertz at the moment, and it's not drawing any current. So let's plug in our power analyzer, and 230 volts, 48 milliamps, and it's also giving us a power factor which is a 0.049, which I'm guessing the reason we're seeing that is because basically this thing is just going to be presenting a very capacitive load, because that's what it's got inside. It's got a big capacitor. So what I'm guessing it's actually showing is this meter reading here, this 550 milliwatts. I'm going to assume that this is again, it's showing true power rather than apparent power, which would be just volts times amps. So this is true power, taking into account the power factor of 0.049. So here's our first set of readings. As you can see, the voltages pretty much all coincided with each other, as did really the current readings. The Avo was kind of a little bit lower, only 46 milliamps, but we're going to forgive it that. Obviously it's not a digital meter, you're trying to read the needle, the scale off the needle. You're trying to read the scale off it. Could have been a little bit of parallax error, it could be slightly out of calibration. I think we can forgive a couple of milliamps for a 50-year-old meter. Now what I've put in this column here is just the VA of the measurement, so which probably isn't particularly meaningful, but I kind of done it to almost prove a point, not necessarily to you, but almost to prove a point to myself. So we've 230 volts times 46 milliamps equals 10.5 watts. That times that 10.9, and then 11, 11, 11. If this thing was actually dissipating 11 watts, it would be getting hot, and it isn't. It's stone cold. So what I think that shows us is the 0.5 watts, which the Exotec was saying it was drawing, which is a true power measurement. That's really correct. And now I know everybody knows the difference between true power and apparent power, but it's not something I necessarily deal with every day. And yeah, I was kind of quite surprised there. For you know, a capacitive load, you can be drawing 48 milliamps, and you can be at 230 volts, and you think you're at 11 watts, but yeah, you're not at 11 watts, you're at 0.54 watts. So I'm not even going to say a trap for young players. I mean, I think everybody in electronics knows that. But if you don't play with these things every day, you know, those bits of those bits of knowledge, they kind of gather dust. So it's quite interesting to play with things like this. You've got to blow the dust off from time to time, haven't you? That's what we do. I'm just blowing the dust off. Right, okay, so we've got to change our test setup now, because the next thing I'm going to use to measure the voltage and the current is the TDS 2022B, which is a Tetronic oscilloscope. So it won't be too difficult to measure the voltage, although I am going to measure it using a voltage divider just to limit the amount of voltage that the scope sees. But we're actually going to get the current measurement by dropping the current across. We're going to develop a voltage across a load resistor, a shunt resistor, and that's going to give us a milliamp reading. So slightly different test setup. Let's go ahead and set that up now. Well, we've got our oscilloscope plugged in now, and hopefully you can read the screen. We've got the sinusoidal input wave, which is being derived from the isolation transformer, then the variac. And again, I've set the variac to approximately 230 volts output. Now, just so you can understand what the where the readings are coming from, I think we're on. We got that. We're on a times 10 probe. We're on 50 volts per division, and that's including for the times 10 probe. So you don't need to do the maths on that. But if you can see, we've actually set up the scope to produce an RMS cycle there at 116 volts. Well, you kind of wonder, if you're wondering why that's not 230 volts, it's because I'm actually using a potential divider, a couple of 10k resistors, because this the maximum input I can go to on this, we're using time 10s probes, is 50 volts per division, which wouldn't allow us to show the full waveform unless we use this potential divider. So let me just show you that. So trying to be relatively careful I don't touch anything. We've got the main supply coming in on these two terminals here from the transformer, and what we're actually doing is across the mains we've got two 10k resistors, and then the center point of those two 10k resistors we've got going to the input of channel 1, which is the yellow trace. Now we're actually feeding the output to the plug socket here, the output socket. We're actually feeding that via a 10 ohm resistor, because what will happen is any current that we're pulling through this resistor here will get, I don't know, what do you call it, transposed into a voltage, and then we can use the oscilloscope to actually measure the voltage, and if we know the voltage we can drive the current by using simple Ohm's law. So that's all perfectly obvious. Some of these readings will be a little bit screwy because I'm measuring the incoming mains here, but we're going to kind of have this burden voltage being dropped across the resistor. So depending on what the current is, we're probably going to be a few volts out on some of our readings, but I'm just going to ignore that. I don't think it really matters. So here's our nice incoming main sine wave. We're measuring it as 116 volts. Well, again, we're measuring half because we're in a potential divider. Multiply that by 2 and we get 232 volts. So yeah, all good stuff. 326 volts peak to peak there. Again, have to double times that by 2 as well, wouldn't we? So good stuff. But really the interesting part will now be to look at the current waveform. So as you can see, the interesting thing about the current waveform is it's actually out of phase with the voltage, and that's because we've got a capacitive load. So before, when I was doing the milliamps times the volts, that was an incorrect thing to do. That was wrong, because the voltage and the currents, they don't line up with each other, they're out of phase. So maybe the average voltage was 230 volts, but the current is at a different point in its cycle, if you like. It's a different, the timing is out. I don't know the best way to explain that, but yeah, they're not in phase with each other. So what you would actually have to do is, this phase difference is really what's generating that, gives us the number for that power factor, is, you know, it's the difference in phase. Well, I was hoping just to get the RMS average using this cycle RMS function on the scope, but I'm guessing it may be these little kind of noise spikes we're getting coming in. But basically the scope doesn't like doing this RMS cycle measurement. I'm not sure why, but it's just flicking around, so I'm not exactly sure what it is. Oh, we're going to have to get medieval on it. 1, 2, 3, 4, 5, 6. Oh, I'm going to call it 6.5. 6.5, 6.5. And we are on, what are we on? 200 millivolts per division. And I'm going to pretend it's a sine wave because I think, yeah, it's probably the best thing to do. Again, that's the problem. It's not a sine wave, which is part of what this video is about, and that's why we're having all the problems. Anyway, but we'll assume it is a sine wave. 0.65 times by equals 4.5, 0 equals 0.45 volts, and 0.45 volts over a 10 ohm resistor. So divide it by 10 equals 45 milliamps. That was hard work, wasn't it? So I think what I'd like to have a quick go at, if I can remember how to do it, I think I would quite like to have a go at just working out the power factor longhand. So I think to do that we've got to work out the phase shift time. Right, so what I'm going to do is I'm going to try and measure the difference in phase between, well, I'm going to measure the difference in time first, and that's going to give me the phase difference. So I want to measure the difference in time between that, and we could just count up the divisions, but I'm going to try and be flash and have a go with cursors. Let's see if we can zoom in. Can we get any better on the time base? This scope is slow as a wet week. Is that going to do something? Right, okay. So, in fact, the two cursors have pretty much come together there, haven't they? So, let's see if I can move that one over to our zero crossing point. That one's at our zero crossing point. I'm going to write that time down. What is that? That difference in time between the two cursors is 5.720 milliseconds, and we've got to divide that by our cycle time. And I'm not going to bother measuring that. I know that I guess everybody in the UK will know that our cycle time is 20 milliseconds for 50 hertz. So I'm not going to measure it. I'm going to guess it. I'm going to write 20 milliseconds and calculator time, I guess. 5.72. We'll ignore the milliseconds bit because we're going to be in the same units. Divided by 20 equals 0.286. Now we need to multiply that by 360, and that's going to give us the phase shift times 360, and that's saying my phase shift is 102. So again, I'm going off memory now, so I think I need to do the cosine of 102, don't I? So cosine 102, oops, not 1.2, cosine 102 equals 0.2. Anyway, that's what I've done. Tell me if I got it right, have I got it wrong, is it garbage? I'm sure you'll leave it in your comments. Right, so we've got to do everything we've just done, or have a go at doing everything we've just done. We've got to repeat it all for using the inverter plugged in. So without losing the will to live, let's do that.